Good afternoon. Some people are showing up, joining us. I wanted to just start streaming on time to respect people's schedules. I've been asked whether I would hold the lecture during the class time, and I wanted to say I'm trying to reserve the class time, the 6 till 9 slot on Thursdays, for the purpose of quizzes and tests. All right? So if you can't make any of the or some of the 5 to 6 lectures, that's fine with me. You can watch them afterwards, and if you want to participate, you want to be involved without being there, send me your questions in advance and I can address them during the discussion, during the presentation. If you want me to keep you anonymous, I'm starting to think maybe you're scared of sending me questions because I broadcast your name. If you want to remain anonymous, then just let me know and I'll just put up your questions and share them with the class. So you can let me know who's there. I wanted to go back because yesterday I started in the middle, what seemed the middle, with like an overview. I call it the overview. There's actually a document that I placed in the Moodle platform called Unit 4 PROB Overview, and you will see the same questions that we tackled yesterday are laid out there in the same way, so you have a second shot at answering those. I already gave you the answers. I don't know if I'm going to have time to put them up in the Moodle page, but if you want that, let me know. I can maybe at least print it up by hand and upload it. So after the overview in the platform, I have several videos that I've used to address some of the topics in the unit. But I'm going to go back to the beginning just to talk about what probability is, and we've taken for granted, or I've taken for granted, that you understand the concept of probability as a proportion. So when I presented probability to you in the normal distribution unit, I presented the idea that probability, proportion, percentage should all be interpreted when you see the P symbol. When I write Px greater than, little x, or 5. Okay, something like that. So you're supposed to interpret that P to be the proportion of observations or the probability. So the reason why I rationalized you can also call it probability is because the density curve represented the distribution of the population, right? We talked about the idealized distribution as though we had more data, or all of the data possible, to see a pattern in the distribution. And from there, if I take and I look at certain observations showing up or not, what I'm talking about, if a portion of the total possible is what I'm talking about, then I'm really talking about the chance of something, of seeing something or observing a certain outcome. All right, so let's get a little more specific. Again, as I said yesterday, when you think of probability, most of us have an intuition for probability, and I'm going to count on that intuition, and then I'm going to clarify some of the misunderstandings with probability. And you're going to realize that you by intuition, you understand this probably 90%. But I'm going to recap, do an overview of the rules of probability. But let's begin first with a discussion of what is probability from I'm going to take a different angle. Think about the concept or the random event of flipping a coin. So one coin, that's, we'll say a balanced coin, has two possible outcomes. Either if you flip it, it can land on showing heads, ahead, or it could land showing the tails. That's what we say, heads or tails. Right? So you have the head of some historical figure on the coin, and on the other end, the non-head side we refer to as tails in English. So when you flip that, the probability of seeing a head is equivalent to the chance of seeing a tail if the coin is balanced, right? And since there's only two possible outcomes, and they're both equally likely, because that's what we'll assume, it's balanced, so they have equal chance of occurring. And since the sample space of possibilities, head or no head, the total probability of the sample space or any possible outcome coming up is 100%. That means that each outcome has a 50% chance of occurring. So maybe I said a lot more than you need, because intuitively you know there's a 50% chance of a coin flip turning up to be a head. And 50% that the coin flip will turn out to have a tail facing up. Okay, so sure, that's it. You can think of it and leave it there. Or I can ask you to think a little bit deeper about that. What if there was an incident where, say, your family member or friend came to you and he said, he's a little challenged with the notion of probability, and he said to you, well, I'm at home, I'm in quarantine, I had nothing to do, and I was just flipping a coin. I wanted to see if half of the time I saw a head and half of the time I saw a tail. So I flipped the coin 100 times. And you know what happened? Every single time I flipped the coin, out of 100 times, it came up heads. That's perfectly possible. It could happen. But now the question to you is, how do you rationalize probability, the fact that, how do you reconcile that outcome of 100 straight heads with the fact that he should have seen half of those as heads and half of those as tails? Where is the 50% when 100% of the outcomes turned up heads? So let me show you here what an experiment that you could do, and it will reconcile this idea. So essentially your answer to the person, if they were to put you on the spot and ask you, well, where's the 50%? The answer, the response to them is go back and keep on flipping. In fact, it takes many trials, many attempts, many observations to, or what we call the long run outcome, to demonstrate probability. So for instance, here what we have is a depiction if this individual was to go back and do that, what I suggested, just keep on flipping. It's like if he flipped just once, and got ahead, then in this chart you would plot, you know, he would plot here that he got one head. That was a very big circle. Okay, and let's say so it's 100% of the outcomes, just one chance, it's 100%. One out of one turned out to be heads, so it would plot here. Now that's in this try, when this individual goes back and tries this on his own. It could have gone differently. He could have ended up with a tail, so the drawing would look slightly different. But bear with me. It doesn't really matter what happens when he's just flipping a few times. What's more important is if he's tossing the coin or flipping it many times. Let's say he flips it 4 times. Or 3 times. So let's say this is 3 times here. So this is 3 flips. So here, whereas here it was 1 out of 1 heads, it turns out here that only 1 of 3 flips turned out to be a head. So that's 30%. So that's what's plotted here. This is like 33.3%. Here's 6 times. So that's 6. Let me put these here. So this is like 3 times, and then this one here is like 6 times. The chart really isn't to scale, but I'm trying to illustrate so you can use this to recall what I said. So here, if in 6 flips, 4 of them result in a head, 4 out of 6, then that's going to be 4 out of 6 is 66.67 or 66.7. So that's about here, okay? To keep on going, the more you flip, so here's 10, and out of 10, it was like 6 out of 10. That's 6 out of 10 there. So let me mark them. Yeah, those that's just marking the spot. So 6 out of 10 were heads of all of the flips, of all the tosses. Oh, sorry, that was 6 here. No, sorry, 6 out of 10 was here. Okay? But what's going to happen if you toss more? So here are 50 tosses and 100 tosses and 500 tosses. After about somewhere after 100 tosses, so in our case, the example that I gave you, he tossed 100 times and got 100 heads, so it would have been another peak up here, which is unlikely, but it could happen in one of the iterations of this. No, it would have been there, but not in this diagram, so I won't put it. These kinds of empirical studies were conducted by statisticians to illustrate probability in action. So they could explain to people, because people could try this on their own, given time, and then when computers were developed, they could simulate these outcomes and show that probability, the 50% of tosses turning up heads, will be the case as long as you flip it enough. So after about, somewhere after 100 flips, you're pretty sure at 500 flips, 250 will be heads and 250 will be tails. Okay, so this is why we say that probability is the same as long run outcomes or long run relative frequency. These are relative frequencies, right? When I divide, I say 6 out of 10, that's a relative frequency. Out of 10, 6 turned up heads. This one as well. Out of 6, 4 turns up heads. So those are relative frequencies. The long run is over here when I'm flipping many times. I've seen many I've observed many iterations of the experiment, and it's revealed the 50%. Right now we're seeing a lot of data in the media about regarding the infection, number of people or cases, people infected with a virus. And there's various ways of looking at that information. But don't be misled. Don't be misled by medical statistics when marketing, for instance, will say things like, or marketing campaigns will try and simplify, and they risk oversimplifying notions like your risk of contracting the virus or being infected is 1 out of so many. All right? Unless they're talking, the so many that they're referring to is out of a large number of trials or out of a large number of individuals, it's probably not so easily, it's not so well interpreted. Okay? So what they'll say are things like, for instance, they'll refer to cases as something like 4 per 1 million population. That's the same idea. It's talking about the long run relative frequency. You have to observe, in other words, 1 million people to see the rate of infection is 4. Okay, so you'll see 4 per 100,000 population. That's another common one. All right, like 4 per 100,000 population. Something like that, where the K represents thousands. Okay, so that's why they say it like that, because they're referring to the probability and the chance in terms of probabilities that are long-run relative frequencies. Okay. So just to bring this home, you might hear that 1 in 3 men will have experienced prostate or cancer in their lifetime. You might hear something like that. You might come across a marketing campaign to raise money for research. 1 in 3, or to encourage people to get their to get follow up with their doctor, or to get screening done. So you'll be told 1 in 3 women, 1 in 3 men develop some sort of ailment. But does that mean that if you take 3 women in your family, one of them is going to have an adverse, or a health problem, or a case of cancer? No. Okay, that's not how you interpret it. It's a way that marketers try to elicit emotion and persuade people to act. However, those numbers come from large population studies, and really you would have to say if it's 1 in 3, then what they're saying, or sorry, 1 in 3, then it's really they're deriving that from a larger population. So it's more like 100,000 and 300,000, which is, yes, okay, that's still 1 in 3. But to observe probabilities, you need to see many trials. There needs to be many incidences observed before you actually it exhibits the long run relative frequency or probability. Okay, so that's what I'm talking about there. Then I get into some terminology of probability, and I demonstrate with some examples. I demonstrate really that your intuition about probability is going to be your it's going to be a crutch. Like, you're going to count on your intuition of probability. But we need to just correct a few things, tweak a few things in your understanding of probability to do well in this unit and to understand this course, because really, if normal probability or normal distribution is going to be, I told you that Unit 3 was the most important unit of the whole course. It's that the material that we covered in Unit 3, you're going to use again and again until the end of the course, so you're not allowed to forget that information. And you should be, if you haven't resolved questions or problems you have with normal distribution, please contact me so I can help clarify misunderstandings, because you need that. You need that skill, that tool. So probability, similarly, it's going to be a launching pad for what we're going to do with the normal distribution in terms of deriving estimates. So with this example, I'm going to outline some of the key terminology in this unit. We're going to talk about the probability of a compound event. What's a compound event? The probability of an event is determined by considering the event's representation in the sample space of all possible outcomes. And I refer to them as singular outcomes. So for instance, we refer to the random experiment of flipping 4 coins. So not just one, we're going to flip 4. The random variable in that experiment is going to be capital X. Now, I use X, and textbooks will use X. What's really important is what X means, okay? So I could use X to be a normally distributed variable. In this case, X is not. It's the outcome of flipping 4 coins, which is discrete. It's not continuous like a normal distribution. So this is a different kind of distribution now we're going to deal with, and we're going to talk some about different kinds of distributions shortly. So the possible outcomes of flipping 4 coins are listed here. I've just listed them. Now you could do this. You could make a list like this for yourself. I illustrated below how you might do that. Okay, well, ignore the example, but to actually make the list, to create the list, you can, think of all the iterations, all possible permutations of tail and heads in 4 tries. That's what it's called, permutations. All the arrangements. So I've just listed them here. Now, there's no reason to think any one of those outcomes is more likely than the other, is there? In fact, let's think about it for a minute. Here's So here's 4 possible. Here, what are all the possibilities for trials? Repeating, flipping a coin 4 times. Well, in the first try, you could get a head or a tail, right? So there's 2 possible outcomes. On the second try, it's still 2 possible outcomes, head or tail. What I got on the first try is not going to affect what I get on the second. I'm just looking for all possible combinations or arrangements. In the next subsequent try, flip, toss, there's again 2 possibilities, head or tail. And same with the last one. So if this is familiar to you, you learned this in high school. If it's not familiar to you, you maybe missed that day in class. It's really important that you understand where or how to think about rearranging these possible outcomes. So it can be head or tail here, head or tail here, head or tail here, head or tail here. So that means you have 2 times 2 times 2 times 2 possible outcomes, or 16. Okay? Now you can do that mathematically, or you could sit there and try and list it out and prove it to yourself, but that's how you figure out in advance how many you're looking for. Okay, so this turns out to be 16 possible outcomes. Here's the list here. And I refer to this as a sample space, and what I do is I use curled brackets. I'll expand this a bit. Right, curly brackets to enclose all the possible outcomes. The sample space, the outcomes in the sample space, their probabilities should total 100%, just like you should be thinking of the density curve. So since that's the case, and there's the total sum of all of these should be 1 or 100%, that means 1 out of 16 should be the probability of each, because 1/16 times, or 16 times, is 100%. So all I've done here is illustrated how you can set up an experiment or a phenomena to look at these events. I've listed all the possible outcomes for this variable that I've defined, and then I know the probabilities. So when I do that, when I make a list of all the possible outcomes and I provide its probability or the probabilities of the outcomes, that is called a distribution, which we learned in the unit for GDS, graphing and descriptive statistics. Okay, so that's the distribution. It doesn't look like the distributions we've been looking at till now, because this is an example of a discrete distribution. In a discrete distribution, I'm actually listing all the possible outcomes and their probability, right? So in a continuous one, like the normal, we usually use a drawing to display the likelihood of certain outcomes, because we can't show the probability for each value. Remember, because the probability of each value, if the random variable is continuous, is going to be 0. So you can't display that. Here, the probability of each outcome is an actual value. So that's the difference between discrete and continuous. Also, along with that, if you want to if you were to list all the possible outcomes of a discrete distribution, you can do that because it's finite. But for a continuous one, you can't, because it's infinite. So we don't make a list. We use a drawing instead in its place. A sketch. Now we can sketch this too. There's no restrictions on that, and I'll talk about that in a bit as well. Okay, so how do we use this? I just make a point that, our goal is, always back to our goal, is to use statistics to alleviate uncertainty. When we want to know something about a variable, the variable here is the outcome of flipping 4 coins. These are the possible outcomes. I've narrowed it down to 16, so I know what to expect. It could be more interesting if I define a new random variable. That's what I'm going to do below, related to the one we just discussed. This new random variable, I'm also going to call it x, but it has a different definition. So x is just a place mark, okay, for variable. I use a capital X, remember, because I'm referring to the random variable, not exactly the values. Not yet. So we can recast this variable, the variable we talked about, as this variable, as the number of tails in 4 flips of a coin. What are the possible outcomes of the number of tails? Well, you can have 0 tails, 1 tail, 2 tails, 3 tails, or 4 tails, and that's how you would group the 16 possible outcomes. I don't have any new outcomes. I've just grouped them and redefined my variable. From there, I can make a distribution. I need to calculate what the possible outcomes, the probabilities are. So I'll do that here. Since each one is 1 out of 16, then if I group them, the probability of 0 tails is 1/16. However, the probability of 1 tail is 1, 2, 3, 4/16. How am I doing that? How do I know that? It's intuition, right? Remember yesterday we discussed what's the probability of this event, seeing this outcome, or this outcome, or this outcome, or this outcome. If someone asks you about this or that occurring, you sum. So it's going to be 1, 2, 3, 4. They're all worth 1/16 or have 1/16 chance. So it's 4/16. And similarly, this is going to be 6/16. This is 4/16. And this is 1/16. And now I'm going to place them in a table. And see, this is the probability distribution for that variable x. You can enter the results here. This is just to show you how I would write it. I could write it as the probability of 0 tails, Or I could also use this notation that looks familiar. This is similar to what we used for the variable that was continuous, the normal distribution. But remembering x has been defined now as the number of tails and 4 flips of a coin. If it was continuous, we wouldn't get an answer for x, probability of x equals 0 or x equals 1 or x equals 4. The answer would just be 0 for all of those, but because it's discrete, we actually can calculate this. And so the numbers that we got there, this is 116, this is 416, this one is 616, and then 416, and 116, and then I transfer those numbers here, and I make them decimals. If you like decimals, you can use decimals. If you like fractions, stick with fractions. I think most people prefer decimals, but they appreciate fractions. So I put both. All right, so we have the distribution. I'm showing you here all the possible values and their probabilities, and I show you that they sum to 1. Okay? Now, like the standard normal table that we were using to calculate probabilities of certain outcomes, if the variable was normal, I'm going to use this table in a similar way, but for this variable that is discrete. I can create or compound events. So this is the heading of this discussion was compounded events. So here's a compound event. Not looking at the singular outcomes 0, 1, 2, 3, 4, 4, I'm going to combine them. So what's the probability of at least 2 tails? At least 2 tails out of all the possible outcomes. So I'm going to use this tool where I list all the possible outcomes and I isolate 2, 3, and 4. So that could be written as, this would indicate to me that you know what I'm asking. So I would be happy with that. Or you can write it like this. Greater than or equal to 2. And this would equal to, how do we do this? We have to add this, this, and this, again, with the notion that we're saying we want probability x equals 2, or, which is plus, x equals 3, or x equals 4. And you sum them. You sum them up. So these added together makes 1116, or in fractions, in decimals, you guys can figure it out. What about less than 3 tails? Less than 3 tails means they could have gotten 0 tails, 1 tail, or 2 tails. That's less than 3, right? Not including 3. So that would also be that's less than 3. So it looks familiar because notice the distribution is symmetric. these are the same, these are the same, and this is different. Okay, it's a discrete distribution, but it's symmetric. It's symmetry. It's, in other words, there's a mirror through the middle. Whatever's happening in terms of probabilities over here is mirrored over here. So I get the same thing. 11, 16. And finally, less than 1 tail or more than 3 tails. You can write it like that. You can express it by listing the possible outcomes of X and then identifying the ones you need to calculate. Or you can show the probability form of the solution. So this is what I'm looking for. So what I have to do is add this one and this one. That's the probability that X equals 1. Notice now that I've done this many times, you should notice the little x is here. These are the values. And then this says probability that the variable, the big X, equals the value. Okay, so it's going to be just 116 plus 116, which is 216. And some people might ask, do I have to reduce anything? No, I just want to know you know what you're doing. You don't have to do any fancy presentation with the math there. If you like fractions, convert it to a fraction. It's fine with me. So, from that illustration, we understand an event as any collection of results or outcome of a procedure. In this case, flipping 4 coins. A simple event is an outcome or an event that cannot be further broken down into simpler components. A compound event is a combination of those simple events. And I'll never test you on this terminology, it's just so that you can read through the notes. I've just provided the definitions here. And remembering the sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. Let me just say what I've done. All right, so we want to recap what we've discussed today and yesterday and tie in your intuition in a systematic way. I'm going to cover the 6 probability rules that are the foundation for probability theory. The first rule is that any event, its probability will be found between 0 and 1. Okay, so there's no negative probabilities. There's no probabilities greater than 100%. We have that intuition. We understand that probabilities are between 0 and 1 inclusive. They could be 0 and they could be 1. Rule 2. All possible outcomes together must have a probability of 1. So this is the probability of the sample space. Notice sometimes I say PR and sometimes I use P. They are the same thing. Probability. The third rule is the complement rule, which you've seen in action, which you've actually applied. The complement rule for 2 complementary events, 2 events are complementary if only one of these 2 events occurs at any time. So that's a nice definition that aligns with this graphic, this Venn diagram. we I used an example yesterday, and I used A and B, but I want to be a little more specific. I don't know. Let's be efficient. Is using one event A, and its complement is AC, A complement. Right, so that's the notation that can be used. So I'm relating A back to A complement and vice versa. And these two complete the space. So only one of those two can occur. So this was the example of rain or no rain. You can also think of the example we just discussed about flipping 4 coins. I could define an event out of all those possible outcomes. I could say, let's define compound event A as no tails. Then not no tails would be all the other possible outcomes. In words, that would be at least one tail. Okay, so that's terminology I can use to refer to the complements. You should get familiar with this terminology because you have to solve problems using these adjectives. I could also, I give another example here. We can define a compound event B, which is one tail. Then not B is all the others. What are the others? Well, 0 tails or at least 2 tails. Okay, so you should just think of the possible outcomes to help you. The possible outcomes are 0. Let me make that. The possible outcomes are x equals 0, 1, 2, 3, 4. Okay, so it can be from 0 tails to 4 tails and anything in between. But if I specify event B as 1 tail, then not B is all the other possibilities, which I can simplify in words as 0 tails or more than 2, or at least 2. Okay. Rule number 4. We saw this yesterday too, but I didn't refer to it as the rule, but here I will. Rule number 4 is the addition rule for disjoint events. Remember this graphic, this Venn diagram for disjoint events. Remember, disjoint events are not complementary. It means it doesn't fill the whole space. Either A, B, or something else can happen. If this is the case, then if you wanted to know the probability of A or B happening, all you have to do is add them. It's very, very straightforward. And I ask you to refer, for an example, back to the variable, to the random variable, the distribution we already discussed. That's what we were doing to calculate the probabilities all along. We were just adding the probabilities of the events to calculate the compound events probability. Okay, so we've done 4 of, we covered 4 of the probability rules. I provide an example. This is an exercise. I discussed something like this yesterday, but I didn't put numbers on it. A is the event that a doctor is in his office at 9:30. B is the event that he is in the hospital at 9:30. So I've gathered from that, I've defined A as the office and B as the hospital. And I've written down their probabilities for you. And now I ask you the question, what is the probability that the doctor is not in the hospital? Well, the probability that he is in the hospital is 27. So not probability of not B is 1 minus probability of B, which is 1 minus 0.27, which is 0.73. All right, so I use the complement rule for that. What is the probability, this is the second question, what is the probability that the doctor is either in his office or in the hospital? So either or is probability of A or B. Again, you have to get used to these word problems. And for probability A or B, we just sum using the addition rule, rule number 4, for disjoint events. So when you sum these two, you get 0.75, right? Notice it's not 100%. It doesn't fill the space completely. And finally, if the doctor didn't go to his office or the hospital, so this is actually the negative. This is neither nor, For neither nor, what we're asking for, like we did yesterday, was the probability of not A or B. The probability of not A or B is, again, 1 minus, because the not is the complement. 1 minus probability of A or B. And we know the probability of A or B was 75%. So this is 1 minus 75, or 0.75, which is 0.25. There. Okay, so that's that. We arrive next at the work that we did yesterday. So we've covered 4 rules. There's 2 more, and the 2 more are going to involve these drawings here. All right? Overlapping events. So let A and B be 2 events. With probabilities of A being 30% and B being 40%, and I ask you to find A and B. So that the probability of them both happening at the same time. Now, I haven't explained, I haven't used an example here. It would be helpful to understand how they intersect in order to find the probabilities without any additional information. I give an example on page 9, which I want to discuss now, to help, I hope, help you understand where I'm going with the concept of independence. But first, in general, if I wanted to find the probability of two events simultaneously happening, I would multiply the probability of the event times the probability of the other event, given that one already occurred. This is how I write that. Okay? This is called, oops. It's like a roller coaster. This line here is given. We say given. It's known as a conditional probability. The probability of an event given that one already occurred. Now this should be the same as, in general, this should be the same as doing it the other way with B. What about if I take the probability of B and then I multiply it by the probability of A given B occurred? That should give me the same thing. It doesn't matter which one I use as given. I should be getting the same result either way. Now this is best illustrated with examples. This is the theory behind it. Turns out that in general, you need this extra bit of information. What happens to the probability of B if A is known to have occurred? Or what happens to the probability of A knowing B had occurred? If nothing happens and the probability is still the same, the event, the chance that it happens, the distribution of possible outcomes doesn't change, then these will reduce. We would say that the events would be independent, and B given A would just be a B. And similarly, A given B would just be A. If that's the case, you're talking about independence. So the example that I gave yesterday, let's see if I can remember. What was I talking about yesterday? Well, the example that I want to use on the next page, let's just stick with that one. So this is my example. And I'm going to employ the concept of long-run relative frequency to help drive the point home, okay? Consider there are 10,000 women, and that 10,000 women is enough for me to observe the long-run relative frequency of probabilities of actions of these women in terms of their visiting a salon. So there's two events I'm going to define. One is a manicure. So they're going to the salon to get a manicure. And the other one is they can go there and get their hair colored. Notice the numbers are similar to the ones we used yesterday, or the same, but it's really the example that I want to illustrate as being behind the numbers. So these are two possible outcomes. These are not necessarily disjoint, because when you go to the salon in general, you could have various procedures or various services. You could have manicure, hair color, or something else. You could also have manicure and a hair color. So thinking about this, it's most likely in this exercise, we're going to work with the case 3. What was case 3? Go back and look at our drawings, remember, over here. That's case 3. This one. It's overlapping, okay? The total of the two probabilities don't completely fill the space of 100%, so they must, there must be something else around. But further, I'm going to assume that you can have both of the events at the same time. You can see both occur. So in this example, the women could have both. And I want to know what's the probability of both. If I was told that A and B are independent, then I'm actually looking at case 4. It looks the same. It's an overlapping, they're overlapping events, but they're overlapping in a very specific way. How many women have both their hair colored and a manicure going into the salon? So let me talk a little bit about these 30% and 40%. So let's say I observed for a long period of time women visits to the hair salon. I don't have to watch the women. I could look at the accounting records of the salon, and I could determine from all the clients how many of the total actually had a manicure and how many of the total actually had their hair colored, and come up with these probabilities after a long period of time, right? Because let's say I observed 10,000 women or 10,000 clients. And now I want to know what's the chance of both of them. If my data demonstrates independence, then what can I expect? What does that mean? Well, first of all, 30% of 10,000 women had a manicure. So that means that's how you use probability. So 10,000 of, when I say the word of, I multiply. 30% of 10,000, I multiply. So 30% of 10,000 is actually 3,000 women. So 3,000 women, they're a subset of all 10,000 who actually had a manicure. Now within that group of women who had a manicure, I'm interested in how many also had their hair colored. Could it be that a woman who had a manicure only had a manicure? Yes. Maybe once the woman has a manicure, she's less likely to have her hair colored. Let's say women who've had a manicure no longer do they have a 40% chance of having their hair colored, but because they spent money or they have limited time, they don't get their hair colored at the same time, or there's no facility to do both at the same time. So in that case, in that general case, this probability would have changed. But in case 4, independence, it doesn't. What it means is, if they're independent, it means that of the 3,000 women, 40% also had their hair colored. So I can just multiply 40% of the 3,000 to find out 1,200 women have both a manicure and a hair color. All right, so the numbers, the values that I have don't change. If events are independent, the probabilities, whether I've seen one event already occur, in this case the manicure, the probability of hair color stays the same. In real life, that's not necessarily the case. So someone either has to tell you they're independent or give you enough information for what you're doing to figure out or to know how to compute the probability of one given the other. Alternately, I should finish this because I should be able to do this the other way as well. I should be able to say, well, what if a woman had her hair colored? A woman that has her hair colored there's about 4,000 women that have their hair colored because 40% of 10,000 is 4,000. Of this 4,000, assuming independence, I was told they're independent, 30% of them have a manicure as well. So 30% of 4,000 is 1,200 as well. So either I go this way, looking at the group of women with manicure first, or I can do this, and I can get the same answer looking at the women who had their hair colored first. Okay, so independence allows me to do that. If they're not independent events, I need extra information that will provide me the conditional probability to figure it out. Okay. So I am going to stop here. I want you to read these notes, like I said last class or last meeting. Have a look at these, read the notes, try the exercises as you go. Watch the videos that I placed up there. I have page 10, 11, 13, 17, 18. I have many pages. Oh no, sorry, those are probability problems. So I have, 10, 11, and 13 to help you along before tomorrow's lecture. And I'm also going to lecture on Friday. So have a good night. You can start the homework exercises. I'm going to summarize the last two rules, but you already have a sense of them. I will do that tomorrow. Tomorrow I'm going to post the midterm at 6 and also the quizzes you can repeat. You can send me your handwritten work as evidence for part marks, and you need to send those within the within 15 minutes of submitting the test or quizzes. Okay, you can't send it the next day or the next week. Some students sent me their homework or their written work yesterday. So no, you have to send it within 15 minutes of submitting. So good luck with everything. I prefer to chop up the lectures in pieces and bits of 1 hour each. And let me know if it's working for you. If it's not, email me. Let me know what you need. We'll be in touch. See you tomorrow.